Hi, we are going to take a look at the architecture with a strange name, pipes and filters. This architecture is used in the data processing systems. Arguably, this architecture stems from a Unix pipeline mechanism used for message passing. The standard shell syntax for anonymous pipes is to list multiple commands separated by vertical bars or pipes. For example, to list files in the current directory, retain only the lines of its output containing the string key, and view the result in a scrolling page, a user types the following into the command line of a terminal. The command ls-l is executed as a process, the output of which is piped to the input of a process for grep key, and likewise the process for less. Each process takes input from a previous process and produces output for the next process via standard streams. So isn't it a good idea to use such an approach for the software that we build? Yes, it is, if we have a processing task that we can divide into a sequence of smaller, independent processing steps that are connected by channels. The central concept in pipes and filters is the processing of a data stream. Variants of this approach are very common. When transformations are sequential, this is a batch sequential model which is extensively used in data processing systems. The figure from Microsoft website illustrates the issues with processing data using a monolithic approach. An application receives and processes data from two data sources. The data from each source is processed by a separate module that performs a series of tasks to transform this data before passing the result to the business logic of application. Some of the tasks that the monolithic modules perform are functionally very similar, but the modules have been designed separately. The code that implements the tasks is closely coupled in the module and has been developed with a little or no thought given the reuse or scalability. A solution is required that addresses these issues and decreases the possibilities for code reuse. Break down the processing required for each stream into a set of separate components or filters, each performing a single task. By standardizing the format of the data that each component receives and sends, these filters can be combined together into a pipeline. This helps to avoid duplicating code and makes it easy to remove, replace, or integrate additional components if processing requirements change. The figure you see shows a solution implemented using pipes and filters. The time it takes to process a single request depends on the speed of the slowest filter in the pipeline. One or more data filters could be a bottleneck, especially if a large number of requests appear in a stream from a particular data source. A key advantage of a pipeline structure is that it provides opportunities for running parallel instances of slower filters, enabling the systems to spread the load and improve throughput. The filters that make up a pipeline can run on different machines, and a filter that is computationally intensive can run on high-performance hardware, while other less demanding filters can be hosted on less expensive commodity hardware. Another benefit is the resiliency that this model can provide. If a filter fails, or the machine it is running on is no longer available, the pipeline can reschedule the work that the filter was performing and direct this work to another instance of a component. Failure of a single filter doesn't necessarily result in the failure of the entire pipeline. The figure you see is not the only approach. Here you see another example. Normally, you will have to construct your own pipeline configuration for the given problem. Let's see the example. Probably you wonder, what is that? This is the so-called augmented reality portal. It is a simple toy that is not that simple to implement, and it uses a lot of data processing in the computer vision algorithms. In order to have a stable portal, the video frame must be analyzed to find the feature points and describe them in a special way in order to detect them later. In order to investigate these algorithms, we created software that compares so-called source and target pictures. In this example, we select two similar images, then select the filter to see how it impacts the feature points. After that, we choose the algorithm that works as feature detector. Also, we select the descriptor algorithm. Then we choose the image matcher algorithm, and finally we choose how to visualize the result. So, we have our pipeline configured. Do you remember the example we discussed earlier? The structure is quite similar. As you can see, we also split our pipeline into two chains that can be performed concurrently. One chain for the processing source image, another for processing the target image. Now let's run the pipeline. The boxes blink for some time to show which processing block is being executed. And we have a result. Source and target images presented side by side and the detected feature points. To sum up, we had a large processing task that we split it into several processing subtasks. This way of organization allowed us to change the blocks of the chain easily. We did it by selecting different algorithms. It allowed us to run tasks concurrently and make use of our CPU cores. Now let's dive into the code. This is the solution of the software we just investigated. So this is WPF project, and here we will see how the pipeline architecture is implemented. The core of a pipeline is the iPipeline element. It describes the interface, and all pipeline objects must conform. So basically, every pipeline element will need to have the setInput method and provide the input stream. It will need to have the process method, where the actual data processing takes place. And it will need to have the connect method. So basically, this is a pipe to another filter. And also we need the getResult method that will provide the results that were calculated during the processing step. So let's see how we construct the pipeline. This is our pipeline. We construct our pipeline by adding the elements into our pipeline using the add method. And when we construct the pipeline, we execute the run method. And this method will execute all the filters one by one until the chain of a pipeline finishes. So let's see how it is implemented in the specific processing tasks. So in the folder process, we have descriptors, detectors, filters, and matchers subfolders. As you may guess, these subfolders are for the different operations. So let's open detectors folder and let's open just one of the processing algorithms. So this is a brisk detector. It has the set input method and we get the input stream. It has the process method where we actually detect feature points using brisk algorithm, and we have the connect method. So here we set the input for the next, providing the calculated output. And we have the method to return our output if asked. For different processing tasks, we have the same structure. So let's see ORP descriptor, for example. So as you can see here, we have the same set input method where we receive the input stream, connect method, which is used to provide output for the next filter, and process method, which implements the specific processing task. So as you can see, it is the standardized way to add or remove any new element. Even for the visualization, we have the same structure, and this element can be added to the chain of our pipeline. As you could see, this pattern is easy to understand. It supports transformation reuse and provides opportunities for running parallel instances of Slough filters, enabling the system to spread the load and improve throughput. Also, it promotes resiliency and scalability. There are challenges, of course. Overhead. Reading data from the pipe and writing data to a pipe might include additional computations. Complexity. The increased flexibility that this pattern provides can also introduce complexity, especially if the filters in a pipeline are distributed across different servers. Reliability. It is necessary to ensure that data flowing between filters in a pipeline won't be lost. Idempotency. The same operations with the same data must produce the same result even if they are performed repeatedly. Filters in a pipeline should be designed to be idempotent. Let's review this topic. Pipes and filters pattern can be used when the processing required by an application can be easily broken down into a set of independent steps. This pattern provides flexibility that is required to allow reordering of the processing steps performed by an application, or the capability to add and remove steps. It is easy to understand and support transformation reuse. This pattern allows scalability and improve resiliency. Using this pattern might increase computation overhead and the complexity of the system. The additional effort might be needed to ensure idempotency. As you saw, it is a nice approach. Be sure to use it when appropriate. Thank you for watching.